All right, guys. So to start here, let's go ahead and just kind of start with our poster and summarize where we're at. So there's four steps total in the process of making ATP, and we've got two of them covered. We've gone through glycolysis. So if you want to take maybe like a pink color to kind of highlight your steps here. Okay, so if I say name the step, you would say like glycolysis, or you would say the prep reaction. Those are the major steps of respiration. We've got two more to learn today. We're going to talk about the Krebs cycle and oxidative phosphorylation. Okay, so glycolysis, it's actually 10 steps, but we didn't draw out all the steps, and that's okay. You just need to be able to recognize the main parts to it. That anytime we see a process, we start with glucose, and you can see when we're done, we end up with 2 pyruvates. We've got some ATP being made, and we have reduced some NAD plus to make NADH. So this is glycolysis. You need to be able to tell me where this happens at. So you need to say glycolysis happens in the cytoplasm. So cells don't need mitochondria to generate ATP. All cells have the ability to generate some ATP in glycolysis. It's just not much, though. It's only 4. Okay, so it doesn't get a cell very far or very much ATP. Okay, in this case, when our ATP is being made, we have a special name for it. It's called substrate level phosphorylation. And in substrate level phosphorylation, this is kind of what's happening. We are going to phosphorylate ADP, which means we're going to take a phosphate and put it on ADP, and then that's how we get ATP. And there's an enzyme that does that. It takes these 2 molecules in as substrates. It transfers the phosphate off of this one onto the ADP, and then out we have products come. So it's an enzyme making some ATP for us, which brings me to, let's actually go to our worksheet. Let's go to 2.4 there on the back page. Okay, so this is question number 18. So one thing that we note, this happens in glycolysis, because we made some ATP in glycolysis. And this is also how ATP is made in this third step, which is called the Krebs cycle. And they like to ask that question. Which 2 levels is substrate level phosphorylation occurring? So we're going to say in glycolysis, and we're going to say the Krebs cycle, which is the third step. We'll get to here in a second. And how that happens is there is an enzyme. And again, every step there is an enzyme that does each step. The enzyme can take in these 2 substrates. It pulls the phosphate off of this intermediate and puts it on ADP. And that's about as simple as I can make it. And away goes ATP. Hopefully you can envision then that this molecule goes on to the next step in glycolysis, but it is now missing a phosphate. That one is gone. Okay, so then this just goes to the next step in glycolysis. And that's how we can get some ATP generated. Okay. All right, so we get some ATP being made here. We get some NADHs and our pyruvates. And I kind of left off with, let me hide this. Okay, so our 2 pyruvates, let me move this up. Here they are. Okay, so this is what the 2 pyruvates are going to look like. Do you see that there's 3 carbon atoms? Okay, this one, 3 carbon atoms. And at the end of here, when I diagram pyruvates, I have them as 3 carbon atoms. Okay, can anyone tell me, out of the 12 hydrogens, how many got pulled off in glycolysis? Out of the 12 hydrogens, how many close? Remember when we pull off hydrogens, we put them on NAD+. 2. See that right here? So we pulled off an H, we put it here. We pulled off another H, put it here. So my pyruvates, when I add them all up, I should have 10 hydrogens out of the 12. 2 are gone. Okay, we put them on these buses. All right. Okay, so if you think about these pyruvates, we still have a lot of breaking down of the glucose to do. I mean, this is just basically half of the glucose molecule. We still have a lot of processing. We can still get a lot of energy and use out of those molecules, and that's what we're going to do. We took those pyruvates and we sent them into the mitochondria. By the way, the inside of the mitochondria is called the matrix. I'm trying to find a good spot to put that it's kind of out of the way. So this is called the matrix of the mitochondria. And what happens in that prep reaction is this is where we finally get some CO2 being made. When this carbon atom gets pulled off, so does an oxygen, and then it reacts with another oxygen. You don't have to know that, and that's why it's CO2. And that's why then my pyruvate now looks like this, acetylcoenzyme A. Okay? All right. How many ATPs are made in the prep reaction? How many ATPs are made in the prep reaction? We got any red ATPs there? So your answer is 0. So let's think about why they call it the prep reaction. When you're prepping something, it means you're getting ready to do something, right? The prep reaction is just getting some molecules ready, but we're not actually making ATP out of them, okay? So that's why it's called the prep reaction. We are prepping this pyruvate to get it ready, and now it's ready. Acetylcoenzyme A is going to enter the next step. So the next step we're going to look at, I'm going to go ahead and put it right here. Step number 3, I'm going to write it kind of out of the matrix. This is called the Krebs cycle. But of course, in science, we can give everything 2 to 3 names. So the guy who discovered it, his last name is Krebs. So it's named after him. But the more scientific name that you might see is called the citric acid cycle. So it can be referred to either. I got a problem here. Okay. Now, it's called a cycle because when they diagram it, they like to draw it as a cycle. And there's a reason why. I don't really need to get into it, but ultimately it remakes a molecule that gets used at the beginning. So that's why it's a cycle, because the product of it can get reused here at the beginning for the next acetylcoenzyme A. Okay. All right. Now, this is the main thing that you have to know. 3, 2, 1, 1. If your circle's big enough, put 3, 2, 1, 1 in that circle. I always like to kind of put it inside to keep it so we can organize our information a little bit better because it gets pretty hectic here. Okay? All right. So what's going to happen is from the acetylcoenzyme A, we're going to pull off 3 H's, but we have to put them on the buses. So we're going to get 3 NADHs. So one happens kind of early. We can pull another proton and electron off and reduce the NAD plus to NADH. So that you get another one there. We also get one here at this very end, NADH. So if you didn't see me do that, we get 3 NADHs. So that's where the 3 comes from. Okay. The 2 is easy. Do you see how many carbon atoms are in acetylcoenzyme A? Each one, when we pull off a carbon atom, makes a CO2. Let me go ahead and write up here 3 NADHs. So I'm just summarizing. 3 NADHs is what we're going to get. We get 2 CO2s. That happens pretty quickly here. And you don't have to be able to tell me where. I'm just showing you. Sometimes they draw a diagram of the Krebs cycle like this with these molecules coming off of this circle. So I just want you to have eyeballs on a typical Krebs cycle diagram. Okay. Right here at the bottom, we get an ATP. And we're going to come color code all these in a second. So I'm going to write 1 ATP, 3, 2, 1, 1. And then what the heck is left? So there's a new molecule. It's another bus. So I'm going to color this one in orange because I kind of think of buses as being yellow and orange. So this molecule is really similar to the NADHs, but it's called FAD. And when we load it up, it's FADH2. So that's what gets made is FADH2. Okay, and that kind of happens right here. Okay. All right, let's color code a little bit just to kind of process that. Okay, so we're going to get, here's my 3 NADHs. Lots of yellow. Okay. For my FADH2, because it's like a bus, and remember the NADHs are really just NADs is what they started out with. It looks like this. When a proton and electron are put onto the NAD+, we say it's been reduced to NADH. And that's really similar to what happens to the FAD gets turned into FADH2. So I'm going to put it more of kind of an orange bus, but to keep with that theme, because the buses can pick up things and can take those things somewhere else. Just like buses pick up students and take you guys and drop you off somewhere else, okay? To kind of keep in theme here, I'm gonna grab green. Let's track all of our carbons. So if you remember, we had a carbon atom here, and in the prep reaction, that one got removed. So here goes a carbon atom. Okay. And then these two right here, which are left over, when we took those away, here goes a carbon atom. Here goes another carbon atom. So there's 2 because there's 2 carbon atoms that enter. Hold on, I got a shadow here, so let me move this a little bit so I can get rid of my shadow. And 2 carbon atoms, CO2. And we've kind of been going with red for energy. There's my ATP. 3, 2, 1, 1. You get 3 NADHs, 2 CO2s, 1 ATP, and another bus. And by the way, don't call them buses, but you can call them shuttles. You can actually call them electron shuttles, or proton electron shuttles is a acceptable scientific way to say what these are. They can shuttle electrons and protons. Okay. Now, I'm not going to draw this whole thing out again, but I want you to kind of note here. Remember, we had 2 pyruvates, so both of them made an acetyl coenzyme A. So why don't we just make sure you understand that from 1 glucose, we get 2 turns of the Krebs. We get 2 turns of the Krebs cycle. And write 3, 2, 1, 1 in there. And again, that was 3 NADHs, 2 CO2s, 1 ATP, and 1 FADH2. Okay. All right, so FYI, at the end of the Krebs, glucose is gone. Every bit of it is gone. Every carbon atom has been removed. Every oxygen is gone too. Every hydrogen, these atoms are gone. They're just in other forms, in other molecules now. But glucose has been completely broken down. It's gone. And I can find everything because if I had C6H12O6, I have to have still all of those atoms. And when you go back and you count, I made 6 CO2s. Bam, 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 bam. 6 CO2s. I pulled off 12 H's and I made 12 buses. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. Glucose is gone. All right. How about let's do this. I didn't do this one. This is the very last problem on 4.2. This is number 19. So let's just kind of see what makes sense now. Okay. So first of all, it says identify the 2 metabolic pathways being shown in the diagram above. Do you recognize that? So what is that step of respiration called? Thank you. So we just diagrammed it a different way, but notice we went from 3 down to 2. We were prepping a molecule, means we're getting this molecule ready so it can then be used to generate some ATP. Okay. And then obviously this is the Krebs cycle, is the next metabolic pathway. That's something that I think is also confusing. Remember, metabolism just simply means when molecules are being built or broken down. And so if I say 2 metabolic pathways of respiration, we're talking about glycolysis is a metabolic pathway. The prep reaction is a metabolic pathway. It's just a fancy way to say steps of respiration. Okay. All right. Let's see if we can kind of do B. It says add CO2, NADH, ATP, and FADH2 to the correct boxes in the diagram. Okay. Let's start with the prep reaction here. And let's really think about the main things that are made. Okay. So how did we go from 3 carbons to 2? That means something had to be getting made. Okay. So whenever you remove a carbon atom, what gets made? Thank you. So we can call one of those CO2. And hopefully then that makes sense. Also, if protons and electrons are being pulled off of pyruvate, do you remember that they would be then getting put on the bus, like the NAD plus? And so now the NAD plus is now called NADH. To give you guys a visual of that, let me turn down my sound here, and then I'm going to forget to turn it back up, and then I'm going to yell at you guys for not answering my questions. Okay, so just watch this real quick, just to give you an idea. So this is called the preparatory reaction. There's our pyruvate. So watch what's going to happen. Off goes a carbon. Pull off. So we're going to say it's getting oxidized and NAD plus just got reduced. Okay, simple deal. And all that was happening just right there. Okay. Okay, so I have something funny to show you, just to kind of take a mind break here for a second. And I tell you what, this, oh shoot, hold on. Pause. Okay, go back to here. All right, so I just want to make sure this makes sense to you. So do you see how the acetyl coenzyme A, how on earth do we get from 2 carbon atoms to 6? like somehow we spontaneously generated matter. That can't happen, right? Okay, so one thing I want you to know is you see this molecule, see how there's 4 carbons on it? There's 4 C's, okay? The acetyl coenzyme A gets put onto that. Does that make sense? 4 carbons plus 2 carbons. So this molecule that gets made first has 6 carbons. All right, let me show you something funny. And I'm telling you, if you ever have to memorize these molecules, because sometimes professors will make you know the names of the intermediates, okay? I actually have it pretty memorized, even though like I never have to review it. Like I have them memorized because of this acronym. Okay, the only reason why I'm telling you this is because this legit was printed in a college level biology textbook. And because it was in a textbook, I think it's fair game that I teach this to you. Okay. So the acronym that everybody uses to memorize the names of these intermediates, okay, because this is citrate, isocitrate, this is ketoglutarate, this is succinate. Don't remember the other S though, but that's fumarate, this is malate, and that one's oxaloacetate. Here's your acronym. Cindy is kinky, so she fornicates more often. I kid you not. I had a student bring me his mom's biology textbook because she was going into med school. She was becoming a doctor. And in print, this is what it says to help you memorize the intermediates. Remember this acronym. Cindy is kinky, so she fornicates more often. It'll work. All right. But anyway, I digress a little bit. So really, all I need you to understand is this diagram and kind of what's happening here. Do you see how this one has 6 carbons and this one has 5? One got lost, right? So this, in this step, we must have gotten some CO2 produced, right? If we took off, we lose a C, now this molecule isn't going to have as many C's, right? And then can you see we go from 5 C's to 4 C's? I just want this to make sense to you guys. So obviously a CO2 had to be removed. Okay. All right. And again, you don't have to ever have this memorized, but you need to more know 3, 2, 1, 1. Okay. And if you really want to know, like this is where you're going to get an NADH. There's another NADH here, just to kind of emphasize, you get 3 NADHs. You got the 2 CO2s. You get the 1 ATP. I'm just curious. If I put ATP here, what do you think goes in this box? Oh, sorry, I'm still on mute. Very good, thank you. Okay, because you guys are going to have to read diagrams, and I just need to make sure that they make sense to you. If you want to make ATP, you have to have ADP, okay? And then down here is where the FADH2 comes from. Ta-da! Okay, so there's an important question here, and I think before we write the answer on that question, we need to come back to the, oh, that's not you guys. We need to come back here. If I had another color to use, what would it be? I don't know. I'm just going to make a big deal of it with the color. All right. Remember we said substrate level phosphorylation happens in glycolysis. You see those ATPs being made right here? Same way. Substrate level phosphorylation. Gonna run out of room. Substrate level phosphorylation, TION. So they want you to be able to remember that substrate level phosphorylation gives us ATP in 2 steps, in glycolysis and in the Krebs cycle. And like I said, it really is just this. It simply means that there is an enzyme that can take a phosphate off of a substrate and just put it right onto ATP. Okay, that's your substrate level phosphorylation. All right. So what's the other way? Because we keep talking about substrate level phosphorylation. So there must be another way that ATP can be produced. And I'm going to put it up here so it's kind of out of the way. And there is another way that ATP can be produced. It's called oxidative phosphorylation. Oops. Oxidative. Oxidative phosphorylation. So the phosphorylation means we're gonna put a phosphate on ADP. That's what phosphorylate means. Stick a phosphate on something. And we're going to be able to do that because we're going to oxidize some more molecules. Okay. All right. So that is our 4th and final step. And this one's a rock star because if this one gives you 4 ATP and we only get 2 ATP throughout the Krebs, this sucker is going to churn out about 30 ATP. So this is the big money maker right here. So you might even indicate somehow it's going to generate the most ATP. Okay, now I got to give you an idea of, I got to give you some visuals here. Okay, so let me show you what we're about ready to diagram. All right, so we got the mitochondria, right? Do you see we have the inner membrane in there that's folded? Okay, so let's zoom in. And we're going to relate this to something from the 3rd unit, surface area, folding of membranes. So I've mentioned this before. If membranes are folded, it gives us more area where reactions can take place. You see these molecules right here? Those are embedded proteins, and they can do reactions to make ATP. So if there's folding in the membrane, we can pack more of these into the mitochondria, and the mitochondria can generate more ATP. Here's another good look. See how they're packed? See how those proteins are just packed? When we go to draw it, we're not going to draw them all packed together, but we're going to come spread out a little bit because I have to show you what's going to happen on these proteins. So we're going to put those embedded proteins, and notice that I'm probably leaving like a centimeter between each of these proteins. Okay. And you know what? I'm going to put some more over here just because they're everywhere. And the more folded the membrane, the more we can put them, or more we will have in the mitochondria. And I'm going to name them. Those proteins are collectively called the ETC. The ETC. And that stands for the electron transport chain. The electron transport chain. And when you see these diagrammed on your test, they're going to look more like this. You kind of see the resemblance? 4 blobs in a membrane, 4 blobs in the membrane. Okay? So again, this is more probably what you'll see on a test, but we're really simplifying what they look like here. Okay. A couple other things that I need to label here so you know what I'm talking about. So we talked about advantages of organelles, and we said that organelles provide compartments where we can concentrate and isolate molecules. And that's exactly what we got right here. We have a place where we can isolate and concentrate molecules. And if we do, we're going to get a lot of ATP. So this space is really important. It's called the inner membrane space. The inner membrane space. So if I was going to shade it, which I wouldn't, I could shade it all through here. That is called the inner membrane space. And the inner membrane space is going to be the space between these two membranes. And just make sure you understand what we mean that this is the outer. Remember, the mitochondria has two membranes. This is the outer membrane of the mitochondria. And then aptly named, guess what this one's called? This one's the outer. That one's called the inner membrane. Okay, so we have outer membrane, inner membrane. We're going to talk about the inner membrane space. And then remember, this part is called the matrix of the mitochondria. Okay, because so those, we labeled it right here, that this is called the matrix. Okay, all right. So grab your yellow. Here come the buses. The buses are going to unload what they picked up earlier. And now there's two types of buses, if you remember. So I'm also going to grab my orange here because I'm going to bring my FADH2 to an electron transport chain. And this is what's going to happen. My NADHs and my FADH2s are going to get oxidized. And by the way, that's why this is called oxidative phosphorylation. Because we're going to oxidate these molecules and we're going to use them to phosphorylate ADP. Okay, do you remember what oxidation is? Oil rig. Oxidation is losing. They picked up protons and electrons and now they can let them off. Just like a bus picks up kids and can let them off. Okay, so what happens is it releases its protons and electrons. Buddy.
Oh, you have to send a message to Kim because Juan said.
I will. Kim texted me. I got it. Go do some school.
I did do all of it.
It's all done?
Yes.
Wow.
I'll show you.
Okay, you prove it. Cat in the toilet. Okay. So the NADH and the FADH2 are getting oxidized. They're going to release their protons and their electrons. Okay. Now, the great thing about teaching this now, I usually don't teach respiration now. I usually teach it around Halloween, I guess. So, but it's Christmas time. All right. How many of you guys have watched Elf recently? Okay, come on. National Lampoon's Vacation. Everyone needs to watch that for Christmas. You guys need to put in Elf. That's a classic Christmas movie, right? Okay. So do you remember the part on Elf when him and his little brother are going around town and like having fun and they go to the mattress place and they jump on the mattress from mattress to mattress? Who doesn't want to do that, right? Like that, honestly, if I could say like, what would you want to do for your birthday? I was like, rent a mattress store. Like, let's go. Okay. So I like to think of these proteins as kind of like mattresses and watch what happens to the electrons. The electrons are like ELF. Oh, that's a good one. E for ELF. E for electrons. Bryson, what the heck? Okay, I know. I'll come and we'll look at it. Thank you, buddy. Thank you for doing all your work. You're the best. Peace out. Word your mother. Okay, so the electrons. Okay. So the electrons are getting passed down the electron transport chain. And And that's why it's called the electron transport chain. So this is like Elf bouncing from mattress to mattress to mattress. Okay. Now imagine, think of a trampoline. You know, have you ever bounced someone else? Like you hit next to them and like you send them flying. Okay. That's almost kind of what happens here. The H's are along for the ride and they get thrown into the inner membrane space. So when electrons, and this is the scientific way to say it or to explain it, when electrons are passed down the electron transport chain, protons, or you can say hydrogen ions, are moved out of the matrix and concentrated in the inner membrane space. So if we could pause and take a look at where everything is at in the mitochondria, this is one thing that you would notice. In the inner membrane space, there is a high concentration of all these protons. So I want you to kind of note, there is a high proton concentration in the inner membrane space. Okay, well, there's also a low concentration of protons in the matrix as a result. And if we could let those move, then they would move from an area of high concentration to an area of low concentration, right? Passively, right? It wouldn't cost the cell any energy. And the only place they happen to be able to cross, so grab a red. Let's put a very important protein in there that we haven't talked about. That protein there is called ATP synthase. ATP synthase. You can tell me two things pretty quickly about ATP synthase. One, it's an enzyme because it ends in ase. So it's a protein, and its job is to make ATP. That's why they call it ATP synthase. It's going to synthesize ATP. Okay. Eventually, I'm going to have you guys watch this. It's a wrap. And you're like, oh my God, Miss Winter. No, this thing is like amazing. I'm amazed at the information that they put together in a rap that sounds as great as what it does. I think it was produced by like students at Harvard or something. Okay. So they talk about in this rap, they call it the proflow. That would be the proflow. So the only place that the protons can move from high concentrations to low concentrations is through ATP synthase. That's the only hole for them to get through, that transport protein. And when they flow through, this actually spins ATP synthase. I'll show you a video of it. And as it spins, imagine like a carousel spinning and ADP jumping on and phosphorus jumping on. So there's a P there. And then they fly off together as ATP. So this, and by the way, it's a ton. It's usually about 30. I put an exclamation mark there. It's usually about 30 from one glucose molecule. Sure. Okay, so if you think about it, everywhere in the cell, there's reactions taking place, and those reactions need ATP, right? And to use ATP, all you do is you take a phosphate off and you stick it on another molecule, like a kinase, right? But then the ADP just gets released, right? So when you generate ATP, that just in a cell, there's ADP and there's phosphates everywhere, and they need to come together. And so they're available to be put together, but they can't come together on their own. So there's millions of ADPs and phosphates just floating around in the cell at all times. There's also a million of them together as ATP in the cell at all times. Good question. Okay. Couple important concepts. Let's see what makes sense. Obviously, I have addressed glucose, right? You can see that we broke down glucose through several steps. When we broke down glucose, I released carbon atoms. The 6 carbon atoms got released as 6 CO2s. Have I once talked about oxygen being used somewhere? Have I shown you oxygen flying in to save the day somewhere? I haven't. And I also haven't talked about water. Here's where these two get involved. So this is saved for the very, very, very end, okay? So you know when you go to a trampoline park and they have this rule that on certain trampolines, only one person per trampoline. So you can't jump on that trampoline until a person gets off. Well, these electrons have to follow that rule. So this electron can't flow to the next protein if there's already an electron there. So if there's an electron here, this one can't flow. So all the flow stops and none of our protons can get moved across and concentrated in the intermembrane space. So I'm going to grab purple, and there's kind of a reason why I'm going to use purple. Purple kind of looks like blue. So I'm trying to relate these two things together. That electron, this electron can get pulled off by oxygen. That is a big deal. You will see lots of questions about it. And by the way, they have a term for this. Oh, I don't have any room. I'm just going to put it right here. I'm going to write it in the same color. So you go back up and you look about why these two, why we're writing the same color, is called the final electron acceptor. This is the last electron on the last electron transport chain protein. It has to be accepted by something, or this whole process shuts down. Even our NADH and our FADH2, we made a bunch of them, but they can't unload. So imagine buses pulling up to the school, but they can't drop off the kids because the school is too full. We have to remove some of the kids out of the building for then there to be room for them to release those protons and electrons, okay? All right, now, if this takes on electrons and it also binds to some of the H pluses, because remember the H pluses are flowing in, oxygen and H, I'm gonna grab a good solid blue here. And again, this is a big idea. And I'm going to turn it into a water drop too to help emphasize where water gets made in the process of respiration and why. Why is water a product? Water is produced because oxygen is the final electron acceptor, and it has to remove an electron from the electron transport chain. And when it reacts with it and with some hydrogens, it forms water. And now you know why water is a product and why oxygen is needed. And by the way, lecture 3 is all about what happens if you don't get enough oxygen to your cells. Now, you guys already know that, because how many of you have ever worked out and you've been sore the next 3 days? Everybody, right? Well, you're sore because you're out of shape, and you know that. And what's happening is, because you're out of shape, you suck at delivering oxygen to your cells because your heart is out of shape, your diaphragm, which pumps your lungs, it's out of shape. Your blood vessels aren't equipped for a big blood surge to deliver the oxygen needed. So you don't get the oxygen to your cells to do this. So your cells can't do this. This whole process shuts down. And you have to go to plan B because you aren't able to get oxygen to your cells, okay? Very efficiently. So let's note a few other big deals here. Okay. Oh, I know what I need to talk about. It's wherever you have the most space. Okay, I need to give you another term. I have a lot of space here, but if you have more space, I don't know where you have, some of you might have, I don't know where you have space, but my more space is right here. So I'm going to go with it right here. Okay. And you know what? I'm going to put another ATP synthase because you just need to know that they're all over the place. Okay, so there's another ATP synthase. And we know what's going to happen here, right? The H pluses, they go. Okay. So enlighten me. What is the flow of water called? What is the flow of water called? Just took a test on it. Is my sound off? No, my sound's on. What do we call the flow of water? Say it again. Thank you. Okay. You guys know osmosis, right? It's the movement of water from high concentrations to low concentrations. Okay. Well, this isn't water moving from high to low concentrations. This is a molecule moving, a different chemical. Okay. So the flow of protons to generate ATP is called osmosis, but it's called chemiosmosis. Chemi, like chemical, is flowing. So something different than water. Chemiosmosis. Chemiosmosis is the flow of protons. Remember, that's what's happening. They go through ATP synthase to produce ATP. Okay. Chemiosmosis. That's a term they like to ask you about. So when you see chemiosmosis, I think you'll recognize the osmosis, but it's not the flow of water. It's the flow of these protons. Chemical atoms, molecules can be considered chemicals. Okay, so it's chemiosmosis. Okay. All right. Let's answer some questions. We've got 11 minutes. You know, let's just talk about, let's go look at just this last part. So this is question number 3. It's on page 2 at the top. Okay. And notice how they've drawn. Here's our 4 electron transport chain proteins. You don't have to know that there's 4. There's actually 6, but those are smaller proteins right there. Okay. By the way, sometimes they're called cytochrome C proteins. Have you guys ever heard of cyanide? Okay. So you know cyanide is used in movies to kill people, right? So what cyanide does is cyanide actually hooks on to an electron transport chain protein. And so then the electrons can't flow. So then you can't make ATP and then you die because you can't make ATP. So FYI, that's how cyanide kills you, is it blocks the flow of those electrons, and consequently, we can't then set up that concentration gradient, okay? All right, so 3A, referring to the diagram, what stage of respiration is occurring here? So what do we call the 4th stage? Go ahead and write that down. And the reason why we call it oxidative phosphorylation is because we're oxidizing the NADH and the FADH2. We're unloading them. Okay. Now, I think this is what's kind of confusing about these diagrams, because on the test, so they have to zoom in on them so you don't see where the other parts of the mitochondria is. So to give you some reference, this is the inner membrane. They just zoomed in on it. So this would be the inner membrane right here. So this would be the matrix. What's up, bud?
Can you text her? Because I tried calling them once and they won't pick up.
They won't pick up because they know you're supposed to be in school, so they're not answering right now. I'm gonna be done in a little bit and we'll get you situated. Okay? Okay. Quit calling them. Okay. The outer membrane is here. This is the outer membrane. And again, this is why these questions can seem really confusing because you guys are used to my diagram, but they only will give you a small part and you have to figure out what's going on. You see all the H pluses now are in that inner membrane space, and hopefully this makes a little more sense to you, okay? Do you see how in comes oxygen and away it goes as water? Okay, so since you should be picking up on key things, you're like, okay, this is oxidative phosphorylation. Okay, so it says add a line to show where the outer membrane of the mitochondria would be located. So we kind of drew that in there for you. Label the inner membrane space, because you have to be able to tell me facts like protons, or you can say H plus, become concentrated in the inner membrane space. Okay. We labeled the matrix. Here's a question for you. Is ATP synthase shown in the diagram? Do you guys see ATP synthase in the diagram? So one thing that's kind of, go ahead. Right. So the ATP synthase, they're not diagramming it. I mean, there could be one right here. So if you want to draw like ATP synthase is also embedded in the membrane, I mean, ATP synthase can be here, all right? But how you would know if it's ATP synthase is you have to see a couple different things. Like you would see ADP, sometimes they'll show it like this, ADP getting turned into ATP. So then you would know that's ATP synthase. They also would be showing you things like the H pluses flowing through it. So if you see those protons flowing through it, then you know you've got ATP synthase, because that's the only place they can cross from high to low concentrations. In this situation, they're moving from low to high. Okay, and remember, to move anything from low to high concentrations, that takes some energy. And in this case, the energy comes from the movement of the electrons. So when the electrons move, that provides energy to pull those protons across the membrane and concentrate them, move them from an area of low concentration to an area of high concentration. Okay. Something else that they love to do, they like to bring in ideas from multiple units. So here I just taught you this stuff, but can you tell me this? The matrix or the inner membrane space? Where is it more acidic? The matrix or the inner membrane space? Yay! So this is something I've seen them ask. And by the way, this is how we figured out this happens, that all of the H pluses or most of the H pluses become concentrated, is because we can actually put a probe into a mitochondria, like a pH probe. It's really thin. It looks like a needle. You can put it into just the inner membrane space and it will register the pH, and it's a really low pH because it's more acidic versus in the matrix. Okay. So let's see if you can do this one. This is expect always this question, always. Identify the final electron acceptor in respiration that is shown on the diagram. So which molecule is considered the final electron acceptor? And don't say water, because water can't take on any more electrons. It's the oxygen. So it's trying to show you, this arrow is showing you electrons, so it's 2 electrons, and those electrons finally come down here to the oxygen, and then that's converted into the water. Okay, so that's the question. Expect to see it like in 5 different ways. Final electron acceptor. Because how many oxygens are in water? One. Do you see how this says O2? Okay. And then also, they're just trying to be kind of accurate. Oxygen is never just on its own as one oxygen. It's really unstable, it's highly reactive. So the oxygen that you breathe in right now, it's always two of them together. It's a diatomic molecule. It's always as O2. So if one O2 is used, you actually generate two molecules of water. Does that make sense? One O2 would actually give you two molecules of water, which with the 3 minutes left, I'm going to show you this one. So okay, so watch, here we go. Oxidize. There goes your electrons. Protons are concentrated in the inner membrane space. Watch those electrons flow. Watch those protons move across. Oh, here they come. Here comes an O2 and its posse. See how you get two molecules of H2O. Watch the proflow. Okay, so watch where the protons go. I'm going to hit play here. Watch the protons. The only place that they can cross is through ATP synthase. And no, ATP synthase is not an electron transport chain protein. It never gets an electron. The electrons flow this way and stop here. Okay? And then to put the final spin on this all, I want to show you how ATP synthase actually works. It spins. It spins as those protons flow through it. It spins, it changes its shape, and that shape change is what allows it to take ADP and a phosphate and stick those two things together. And it's kind of crazy to think about it, but you know how water flows through a turbine and spins it, and that produces electricity? Well, this is protons flowing through something, spinning it, and it's providing energy. It's just chemical energy and not electricity. So it's kind of the same process. Crazy how that works. All right. So we're going to pause there. And just so you guys know, I'm going to be talking more about lecture 3 because I'm going to be talking about what happens when you don't get oxygen to be the final electron acceptor. Your cells have to switch over to plan B. And that's called anaerobic respiration. So if you want to get kind of caught up on some notes a little bit, but I'm going to be focusing on the 3rd lecture tomorrow. Okay. And then after that, it's Christmas. Woohoo! I've been really good this year. I know Santa's gonna bring me so much. Now that 2nd grader running around that says he's done with school, like not so much. Okay. All right, guys. We'll see you tomorrow. Have a good day. No, I just sent you an email. I was hoping that you saw it. Did you see it yet? Okay. So can we try to meet from now until 12:30? Okay, awesome. I figured that would be okay for you. All right, let me go ahead and let me close out on some of this stuff because I'm taping and it's